Okay, so so just to give you an overview of what we're going to talking about, Don has given already a good assessment of climate change, so I'm not going to go over that. I will talk briefly about the U.S. National Climate Assessment, which I was a co-author on, and we're going to focus a little bit on precipitation. I'm going to focus on heavy precipitation. I know better than to come to this campus and talk about drought. That would be like, I feel like a long-tailed tomcat in a room full of rocking chairs. Address that issue here. So I'm not going to talk about drought, but I will talk about precipitation extremes in both directions as in terms of what we're already seeing in climate record. I'll talk about matching the scales and variables of climate change to agriculture decisions. That is, if we can't map our climate change information onto decisions, then we've missed the point. So we really need to look at what decisions are made, what kinds of information, climate information, are needed for those decisions, and then how do we bring those together. And I'm going to use a couple of examples on that to show how this can be done. And then I'm going to focus a little bit on this issue of actionable science. In other words, we need to have science that is credible, that is salient, and legitimate in order to make progress in using climate science for making good decisions about building resilience. And then finally, I'd like to talk just a little bit about just a kind of an off-the-wall idea about visioning climate or changes to the Nebraska landscape that take into account the impacts of climate. So the overall message from the 2014 National Climate Assessment was that climate change is happening now, that all Americans are feeling the effect of climate change, that the National Assessment was really the most comprehensive study on climate change, and it has a huge background of information, of scientific information, underpinning the conclusions that it came to, and that it ended on a positive note, that Americans have a chance to influence our future, to reduce heat-trapping gases, and to minimize or at least suppress the most negative impacts of climate change. In a nutshell, if you had only one floor in your elevator and you had to make your speech quickly, you'd use this. Dry areas are becoming drier and hotter, and wet areas are becoming wetter and more humid. So if you think about that, that's a good takeaway in terms of climate change. And you can extend that and think about it in terms of periods. And Don made reference to that a little bit, that drought periods and heat waves are going to, if you're already drier and hotter, then these periods are going to become longer. And similarly, wet periods will become wetter and more humid. And it may be happening in the same place. That is, one year you may get long wet periods, another year you may get longer dry periods. So the National Climate Assessment, the website is here, or you can just Google the U.S. National Climate Assessment. You'll get a well-designed website that really is easy to navigate and to burrow down, to go directly to the Great Plains, directly to changes in Nebraska, and look at what's actually changing. And I'll just quickly go over the 6 key messages. This is for the agriculture chapter. Jerry Hatfield of the National Laboratory for Agriculture and the Environment and I were the co-lead authors on this. The background information there's a technical document for that. It has over 1,000 references. So if you want to look at impact on cattle, or if you want to look at the impact on the water resources or energy, you can go back and look at that. So the messages are that climate disruptions to agriculture production increased in the recent past and are projected to increase further in the next 25 years, and that by mid-century and beyond, these impacts will become increasingly negative. So we see that in the first 25 years, there are some things that are going to be rather gradually changing. There's some that are going to be changing more rapid, but by mid-century, things are going to really be much more severe. Many agriculture regions will experience decline in crop and livestock production from increased stress due to weeds, diseases, insect pests, and other climate-induced stresses. So both the climate in terms of the direct impact, but also indirect impact on those other stressors. Current loss and degradation of critical agricultural soil and water assets by increasing extremes in precipitation will continue to challenge both rain-fed and irrigated agriculture unless innovative conservation methods are implemented. So there's a call already for both rain-fed and irrigated crop agriculture that we need to be looking for solutions on water management. Rising incidence of weather extremes will have increasingly negative impacts on crop and livestock productivity because critical thresholds are already being exceeded. We had some discussion earlier about critical thresholds, that when you have an ecosystem, there's a lot of pushing and shoving for space going on, and that one member is at an advantage and others are at disadvantage because of their near critical thresholds. Well, so even small changes will create impacts on natural ecosystems. Finally, the last two, agriculture has been able to adapt to recent changes in climate. However, increased innovation will be needed to ensure that the rate of adaptation of agriculture and the associated socioeconomic system can keep pace with future climate change. So it's not only the plants and the animals, it's the socioeconomic ecosystem. It's our small towns in rural Nebraska, rural Iowa, the communities that depend on it, the businesses that depend on agriculture that need to be considered. And finally then, climate change effects on agriculture will have consequences for food security, both in the U.S. and globally, not only through changes in crop yields, but also changes in the way climate affects the whole transportation, supply chain for food, including barge transport on our rivers and our highways and our bridges. And I'll show some of that later. So in the Great Plains region, again, now bring into the Great Plains section of the assessment, rising temperatures are leading to increased demand for water and energy in part of the region. This will constrain development, stress natural resources, increase competition for water. New agricultural practices will be needed to cope with changing conditions. So Don has gone over that. This was underscored in the region part of the document. And other figures from the document show, again, some of the things that Don alluded to, that the current 7 days per year average above 95 degrees for this one point here in Nebraska moves up to between maybe 14 to 21, so a doubling or a tripling of the number of hot days with these situation scenarios. And again, as Don pointed out, it makes a difference whether we are going to put ourselves on this low emission path or keep us on the high emission path. And the result, or the reason for this is that carbon dioxide is a long-lived constituent in the Earth's atmosphere. That is, if you're an average, maybe an average Iowan, probably average Nebraskans are not much different. I put in about 30 tons of CO2 into the atmosphere a year. That's what an average Iowan puts in. 30 tons. Now, in 100 years, there's still going to be 10 tons of my 30 tons from 2015 that's still in the atmosphere and still contributing to warming. And in 2215, there will still be 3 tons of my 2015 emissions still in the atmosphere. And that's in addition to what I did last year and the year before. Now, if we try to clean up after ourselves, I mean, there's a lot of forestry done in this state. If I plant a tree, and in a year it grows from this big to this big, that's not going to take up my 30 tons of CO2. So cleaning up after ourselves is a tall task. So the reason that we really need to get on these emissions and to start leveling those off and hopefully moving them down. On the precipitation side, this was, Don mentioned that there's more precipitation in the eastern side of the state, the western side of the state, really big gradient across the state. One of the things that I noted is that the historical amount of precipitation on the 7 wettest days of the year, they average about 0.8 of an inch. And if in the future climate, this could go to increase by 0.2 to 0.4. So that would put this at about 1.0 to 1.2 inches, 7 days. Now, I'm going to come back to that in a minute because we're talking again about critical thresholds, and I want to mention. Well, the Great Plains messages then from the regional chapter, and Don, I think, went over pretty much this already, and you can look this up in the report. It's the same, the Great Plains region, as was previously mentioned. So just looking at precipitation a bit on the seasonality, this is another factor that sometimes we might not think about, that we might get the same annual total precipitation, but it might come differently within the seasons. We'll see this big time in Iowa, and you can see why here from these projections under the high emission scenario. We see winter precipitation increasing in the northern part and decreasing to the south of the U.S. We move into spring, we see this dry region moving northward, the wet region moving, the increase in precipitation moving northward. In summer, the increase or the decrease in precipitation centered in the southern Great Plains, and then fall we start to move back to the winter pattern earlier. So if we look at that, we'll look at that also in a slightly different context here. And this is the number of consecutive dry days would be increasing big time in the southern U.S. and the southwest, not so much in the northern Great Plains. Pretty much the same. A factor that's really we're feeling heavily in Iowa, not so much in Nebraska or the Great Plains, but certainly in this region in the Midwest and on into the Northeast, is this change in the amount of rain coming in extreme events. And this uses 4 inches as a benchmark, but there's been a 37% increase in amount of rain coming in these extreme events. Not quite so much in Nebraska, although the eastern part certainly is and has experienced flooding in the last 3 or 4 decades. And that's shown here. The positive trends in flooding shown by large green arrows, triangles. You can see that we've had this range in this part of the world that's really had these increases in floods, and of course we've had some dramatic floods in Iowa, some 500-year floods in the last 15 years. So let's take a look at a little bit closer look at precipitation, because even though this is, and I'm going to look at Iowa, I'm more familiar with that, but there are some lessons I think that we have also for Nebraska. So if we just take a look at statewide average precipitation, we see that over the last 130 years or so, there's only been a 10% increase. That's not very dramatic for that period of time. But maybe that's not the right metric that we ought to be looking at for impact. So let's look first of all at the number of years above 40 inches. So the high rainfall years, you can see that, yes, the extreme years, they've quadrupled over that period. But if we also look at the dry years, years less than 25 inches, we see that they've also increased. So we've had, it's been an increase in the extremes on both sides. And if we look at another metric, and here I come back now to the daily total, and I'm using 1.25 inches because my soil scientist friends in Iowa say that if we get more than about 1.25 inches of rain, then we get the excess over that's going to lead to runoff. inch and a quarter, the dry soils will be able to absorb that. Get more than that, then you start to get runoff. So that's a good threshold to think about. Well, look what's happening here. This is Cedar Rapids data. I looked at Des Moines and it's the same thing. That we go on in the first half of the record, going back to 1895 to 2007 or 8 in this diagram, it goes from 2 to 13 years when we had more than 8 days, 8 or more days of rainfall over an inch and a quarter. Now, what did that Nebraska precipitation graph show in terms of future increase in daily total rainfall? Went from 0.8 up to about 1 to 1.2. So that means that at least in eastern Nebraska, there's going to be a shift toward more of these, what I've called here, erosion promoting events. Seasonality. I mentioned this earlier, but here's an indication from this is the Iowa case, this is statewide. Spring, summer, fall, and winter, and trends 1970 to 2010. And you can see that we've had a slight increase in spring rainfall and a slight increase in summer rainfall. Those are the seasons when we get most of our rain. In the fall, it has actually declined, and winter, when we don't get very much, it is going up slightly. But if you add these two together, you see we've had a 22% increase in the spring and early summer rainfall, and a 13% decrease in fall and winter. So the rainfall is shifted. Even though there's been very little change in the annual total, there's been a shift, a seasonality shift. So again, we have here, it has a big impact, and I'll show this a little bit later. Another metric that I've looked at here, Chris Anderson has shown me this. This is May-June precipitation. This is Iowa total, spring and summer rainfall. So we got May-June here, we got July-August here. So everything in the Easter egg here is within the 95th percentile. And everything outside is this 90 or 95th? I think this is 95th. Yeah, 95th. So look at the years that have been outside the 95th percentile. 2010, 2011, 2012, 2013, 2014, 2015. Something seems non-stationary, right? So some of them here, 2012, as John already alluded to, is outside the 95th percentile on the low side, and then we've had all of these up here. So when we look at these, we can clearly see there's something that is totally different than it was a few years ago. So here's again another metric that, or the plot that Chris has made. This is a plot of annual April to September. So this is growing season rainfall. This is these are the observations from 1870 to about 2010 here. And you can see that if you look at this black line, you can see that we've had more of these extremes in recent years. And then he took 12 different climate scenarios, global climate model scenarios, and took downscaled those to Iowa and overlaid those. So those are the colorful ones here. And you can see that the extremes are sort of agreeing, and maybe a little bit larger down here, but you can see that as time goes on toward the end of the 20th century, we see more heavy rain events and at the same time more extreme droughts. And I expect that this wouldn't be all that much different if we did this for Nebraska. So it's again this idea of more extreme events, and these of course are the ones that are really have big societal impact. So in our state, we are very concerned about this increase in April-May rainfall, this shift in seasonality. Because if you look at the data here, this is the number of suitable field days, days suitable for field work. And that's when farmers want to get that crop in the ground. If they can't get it in the ground in that period, then either they don't get it in the ground at all or yields are way down. So this has a big, big economic impact. So we see that for every 1 inch increase in April-May rainfall, it reduces the number of days suitable for field work by 2.6 days. A really big impact. We saw this in 2013. Over 700,000 acres of high quality, high priced land was not planted to anything in Iowa. So let's take a look at scales, and we in meteorology think a lot about time scales and space scales on which things are happening. And then let's look at agriculture decisions. This diagram is hard to read. I'll show a close-up of one part of it here, but what this is, this was our the U2U project, USDA project that we put together this diagram, and it's a calendar. So in the interior here, this is a calendar: January, February, March, April, May, June, July, and so on. And it's a calendar on the outside. So here's January, February, March, April. So it goes around the same, and they match up. January here's January here. So these are decisions that farmers make in this band. So they purchase seed. This happens to be corn production decisions for Iowa farmers. Now you could do the same thing for soybeans in Illinois or sorghum in Nebraska, or you could probably make a calendar for raising cattle in Nebraska. So it's decisions that farmers make. And they make them every year about the same time. So they're purchasing seed. Some farmers might be purchasing their seed here in January, but the impact of making the wrong decision is felt sometime later, here maybe April. If they purchase seed that they have to get in the ground before the end of April, because it's a 110-day corn or it's a long season corn, if they can't plant it in May, it won't mature. So if they buy long-term seed and it turns out to be the wrong decision, they pay a big price. But the forecast, the weather forecast that's needed, is not a short-term. It's a seasonal forecast. I'm looking at Guillermo here. He's going to be an expert. He's becoming an expert in seasonal forecasts. So what we need to be looking at then is we need to be looking at the length of these arrows and when they occur on this calendar. If we burrow in on that, so here's the seed purchase, here's the time that the impact of that decision is felt. And the length of this arrow is the lead time of that seasonal forecast. So what we need to be focusing on is not the 500 millibar height, not the vertically integrated precipitable water. That isn't what a farmer needs to make a decision. She or he wants to know how many days of suitable for field work are there going to be in April. That's what they need. So what we need to be doing is we need to be converting something that we can calculate, like soil temperature, soil moisture, evaporative potential, those kind of factors, and then translate those into some decision tool like days suitable for field. That's how we need to make that connection. And we, in the meteorological community, and I speak because I'm in that community, we have failed to do that. We need to be doing that, but we need to be challenged by the stakeholders. This is the decision I make, and this is the time of the year that I make it. And I don't maybe not care about your soil moisture forecast in December, but in February forecast for the spring, that is a big decision factor for me. So when is it made and what variables are needed? Okay, so that's the seasonal forecast here, but farmers make decisions on other time scales. They do marketing all year round. They purchase insurance. And so the insurance is purchased maybe a half a year to a year in advance. And there are other decisions. There are machinery purchases. That may be more than thinking longer term, more than half a year. And they would need then maybe some seasonal forecast, maybe an El Nino forecast. They make rental contracts, they install grass waterways, they make decisions on cover crops. Those might need a climate change, an annual or an interannual forecast of climate. Or they may make really long decisions on estate planning, on land purchase, on installing drain tile, or in Nebraska, installing irrigation, or changing irrigation systems. Those require climate change. Those require multi-year forecasts. So for us in the meteorological community, we need to be mindful of the time scale that various decisions are made and the variables that match up to those time scales. I'll talk a little bit here about actionable science, credibility, salience, and legitimacy. And this comes from a study that we did for the Iowa Department of Federal Highway Administration in connection with the Iowa Department of Transportation. But our document, which is really doesn't compare at all with what you've done here in Nebraska, but we did put together climate change impacts on Iowa. It was done during 2009. We published it right at the beginning of the year 2010. We had some policy or some statements in there. We made the statement, climate change is already affecting the way islands live and work. Without action to mitigate these effects, our future responses will become more complex and costly. The following policy recommendations are offered as initial steps to help safeguard our state's economy, environment, and residents. Iowa policymakers should, we had I think 6. The one that I want to point out here is that we said we would advocate for federal highway construction standards that consider the effects of climate change and encourage the Iowa Department of Transportation to explore the use of interim designs that take into account trends in Iowa climate. Well, the Cedar Rapids flood was in 2008. And in 2000, so we had this kind of thing going on around the state. 2010, just the spring after this report was issued, this is a photograph of Highway 35, Des Moines down here, Minneapolis is up here, Ames is right here, and you can see that, look at the design, you can kind of evaluate this design of this roadway here. If you look closely, it became a low-head dam, a quarter-mile long low-head dam that actually flooded this area and the rest of Ames and did not allow this water to go by. Well, you know, if they had done this differently, maybe we wouldn't have had that, but it underscores the fact that decisions that we're making now, we would hope that these bridges and roads would last for 50, 75 years. So Don mentioned non-stationarity. Stationarity is dead was the word that came out in the Science magazine. And so how do we plan design bridges and roadways for the future that will take into account this non-stationarity? So we conducted this project then for the Federal Highway Administration. It was Chris Anderson from Iowa State, David Clayman from the Iowa DOT, Ricardo Mantilla from the University of Iowa Flood Center. So it was a nice partnership between our 2 universities and the Iowa DOT. And so in doing this, we were very mindful that we had, again, to think in terms of how bridge designers make decisions. And of course, anytime we're dealing with either ASHRAE or the DOT, they have engineering standards that they absolutely have to adhere to. And these were designed for stationary climate. Whether we're building buildings and we have to account for increased humidity and increased cooling demand, or whether we're building bridges. Iowa has 4,100 bridges that they don't want to have to replace every 25 years. So how do they build those in order to meet the future climate? So going back to what the sociologists say about creating actionable science, the methods that we propose have to have credibility. And that refers to how the stakeholder perceives information as meeting standards of scientific plausibility, technical adequacy, sources of knowledge must be deemed trustworthy, believable. Do we have any part of the record that we can test these models out on? Do they build on or extend science that's well understood and reliable? In the case of the atmosphere, we've used atmospheric or fluid dynamics models to build airplanes, and we fly in airplanes comfortably. So if we use those for climate change, why can't we believe those same applications? Salience, it has to be relevant. The information we provide has to be relevant to the decision choices that are being made. We can do a lot in meteorology, we can do a lot of interesting things that aren't really relevant to decision making. And we do them because we can do them, right? But they may not be what the decision maker really needs. So we have to avoid this pitfall of identifying interesting and tractable questions that have little relevance to decision making. It has to be legitimate. It has to be unbiased. It has to be fair. It has to survive in this political climate. So it has to be something that you can negotiate on, that everybody can agree on. So we have to get into the worldview, into the mindset that people have, their own experiences, and start and build forward from their own experiences. So an example here is we chose the Cedar River Basin, the Skunk River Basin, two different sized basins, because we wanted to be able to address the question, well, does this only apply to big basins like the Missouri Basin or the Mississippi Basin? Can it be applied to smaller and smaller basins? So we chose two, we used these, and we then looked at, and we created graphs that were identical to the graphs that the engineers use day in, day out for bridge design. And so this is one of them. They plot, and this is stream flow, cubic feet per second, and this is for the Cedar Rapids Basin, or at Highway 151. And so this is the plot that they make to look at past events, and then they use that for their design criteria. So what we did is we took the climate models and we mapped that onto the same. So with their, let's see, their measured 100-year record, here is the 100-year average, and this is the 95th, the 5th and the 95th percentile. The red dotted line is buried under the blue, but it's there. And so then we did that same metric for the climate change models, and we found that the mean goes up to here, and the 95th percentile goes way up here. So we provide the data in exactly the same form that their engineers are used to seeing. Then we run the data through, this is stage 4 radar data, and then we use climate model data. We run it through the University of Iowa streamflow model, and then we get the comparison with streamflow data. I'm not going to spend a lot of time with that. 19 climate models we used on this. Here's the critical graph. These are the observations, the black. You'll see that this is from 1960 up to 2012, or 13, I guess it was. These are the maximum precipitation. It was the observed one day of the year maximum rainfall at each of those, or the average over the Cedar Rapids Basin. So it was looking for the one day of the year that produces the maximum rainfall. That's the one that they have to target for the maximum flood that they're going to be looking at Highway 151 for the Cedar River Basin. So you can see, you just look at this and you see something's gone awry in the last 10, 15 years. These are real data. This is model. These are observed values. We did then, with the climate models, or 19 climate models, we calculated this same 1 day of the year rainfall maximum, and the red line here is the 90th percentile, and this red line is the 10th percentile, and this is the average. So what you see is this, that here is the within sample. So you see that within this region, the model bracketed the actual observations. Then, and we knew of those, that was prior, I mean, there was, that information was used in calibrating the model, but then we had this out of sample period here from 2000 to 2010, I think it was, that you can see that even in that period, the model was bracketing the observations. So this leads to credibility. This allows us to get in the space where these decision makers are making their decisions, and they can see that, yes, we know something has changed in the last 10 years. And this gives us some credibility. It doesn't guarantee, but it gives us some credibility that the model we're using is legitimate to move forward into the future. The alternative is to just go ahead and use this, extend this out. Well, as a decision maker, that makes you kind of uncomfortable to just do things the way you've been doing it. So, so then we project these out. So then we convert those again into graphs that these engineers are used to looking at, and one of it is the return period. This is a discharge, so they plot discharge versus return period with the data set that they have, and for the past, for the 1960 to 2009, is this black line, and the blue band is the uncertainty of that. And then for the future climate, we get the blue curve here and the dotted lines. So you can look at this two ways. You can say that the 100-year flood of the past is now the 25-year flood of the future. That's easy to understand. Or you can look at it the other way and say, well, if we want to still design for a 100-year flood, then we've got to design for a discharge of 5,000 instead of 3,500 cubic feet per second. Okay, that's something that they can put into their bridge design model and come up with a new design. So we've given them information that they can put into their models and use. And this was for Cedar Rapids Basin. For the Skunk River and smaller basin, it turned out that the 100-year flood is now a 45-year flood or something like that. Again, it's still using their method. We provide a window of uncertainty. It could be that this 100-year flood could give you as much as 6,200 cubic feet per second. Okay, well, just finishing up here, I want to just say I couldn't resist thinking about some things about Nebraska's landscape here. Now, I come back to some work that we did here. I had the very rare privilege to work with Jim Brando, Shashi Verma, Michelle, Takle was here at the time, working on shelter belts at Meade and taking measurements and looking and measuring the microclimate. This is not a Meade shelter, this is a Chinese shelter, but I wanted to show this intercropping situation that is an example of building a resilient landscape. And of course, the work that's been done here in Meade and on this campus is some of the best in the world over the last several decades, actually. But we have now a different landscape that looks like this in Iowa. The trees are quite a bit taller. The stems are a little bit better pruned. But the effect is the same. Everything we learned here in Nebraska, we can now rethink in terms of effect on the landscape. So we've got these wind farms. This one has 200 turbines, each of them 1.5 megawatt. That's 350 megawatt wind farm. And that's going to probably be in your future here as well. So we went out and we took data and we found that the impact of these turbines on agriculture is that it increases the downward CO2 flux. So to an ecologist, that means there's more CO2 coming down. When it's depleted by photosynthesis, the turbines are pushing down more. They're pushing it down from the top, but the pressure fluctuations that we measured here in Meade that occur near shelter belts are also leading to pumping CO2 out of the soil for two reasons. And then other work from Shashi Verma's work here, that this extra turbulence that the turbines are creating moves the plants back and forth and allows light to penetrate deeper into this cornfield. Look at how dense this corn is. And so this was in June. When it gets up to August, it's very, very dense. It's dark down in the bottom under this corn. But you get this extra motion, you get light penetration deeper, you get more photosynthesis. So we see a downward CO2 flux, we see an increased upward sensible heat flux, and we see an upward increase in latent heat flux. These are measurements taken upwind and downwind of a line of turbines. So I'm thinking, what about the landscape in Nebraska? Could there be vast arrays of wind turbines or solar panels around agriculture, around feedlots? We could talk about the effect of these turbines even around feedlots because the turbines create a bluff body to the wind, and so underneath you get increased wind speeds at the surface underneath these turbines. Well, that might be nice for a feedlot. You get more ventilation, or maybe you have solar panels and they can graze. They're not graze, but they can sleep or rest in the shade of solar panels. What would the Nebraska landscape look like? Well, it might be kind of fun to envision. So anyway, summary, climate change will have a major impact on Nebraska. I've shown that already. Higher temperatures and amplification of current precipitation extremes in both directions are likely scenarios. Understanding agricultural decisions and the corresponding climate horizons is critical for connecting climate scientists with decision makers. But this information has to be actionable, it has to be credible, salient, and legitimate. And there may be some multiple land use scenarios that we could create, we could design if we think ahead and we start envisioning what the future could be. Thank you.